Well, all right, folks, I think it's time for us to get started. Welcome back to Bio 1120. So half of you have done the first lab for the class, right? And half of you have not. You guys can talk amongst yourselves and explain all the highlights. I don't think there's any question but that you get more out of the lab if you read the lab before you go in there. So for those of you who have not been to lab yet this week, make sure you look through that first experiment. It literally, no joke, is going to take you 10 minutes to read through the whole thing. Just make sure you stop at the end of the first one, because otherwise you're just going to end up reading the whole thing, and it's just going to take up too much of your time, right? There will be time later to read the second experiment. I learned on Tuesday that the people in the freshman prep lab, once again, were resisting my clear and firm instruction to provide beer to the students in the class. I expressed displeasure with that, and I wonder, for those of you who were in lab on Wednesday, say, was there beer for you? No. Well, here's the thing. I've taken matters into my own hand, right? And this is beer for Thursday and Friday. There's more where that came from, but right after class today, I'm walking straight to the lab, and I'm going to have it set up for you. And damn the torpedoes, right? It's I'm giving beer to people who are underage. That's just the kind of thing I do. There you go. All right. So for the rest of the week, and I'm not sure how to make it up to those of you who have been through the lab already and haven't gotten some beer. Maybe we'll do something later in the semester for you guys, donut holes or something like that. We'll figure something out. Okay, so here's where we're at. Fourth time we've gotten together here. And a week ago today, I promised you that in the course of one lecture, I was going to tell you everything that you would learn that was of consequence from an entire year of freshman chemistry, right? And you may disagree. That's fine. You're entitled to your own opinion. But I think I delivered on that promise. I feel like you guys got all that you really need to know in one lecture from an entire year of freshman chemistry. And the rest now you just got to suffer through. But, you know, maybe it'll help you do well in that class now that you know the punchline and the end of the story. Well, here's the deal. Today, my job is to get across to you in one lecture the entirety of sophomore chemistry. Today we're going to talk about organic chemistry, okay, the chemistry of carbon. And I don't know if you've looked that far ahead, but there is, in fact, a 2-semester course, a sophomore level course in chemistry, that is, I've yet to encounter somebody who looks forward to taking organic chemistry. I've yet to encounter anybody who, after taking organic chemistry, comes and says to me, that was the coolest class I've ever had. It's not just a right state thing. It's just organic chemistry. It's in the nature of that beast. But today, I'm going to tell you in one lecture pretty much everything that's important and of consequence, at least for a biologist, about organic chemistry, the chemistry of carbon. Okay, so that's what's on the outline here. And we do these things in this order because they kind of build on each other. And I also have a chance here this morning to re-point out to you. That's probably not the best phrase, but I want to re-highlight, I want to go back, and I want to remind you about some of the most important concepts. And that's what I'm big on here, concepts. I want to remind you about some of the most important concepts about inorganic chemistry so that you can better appreciate what's going on with organic chemistry. And that means I'm going to talk just a little bit about some of the stuff. I'm on. Oh, am I even? Is the keyboard not connected today? That would be a bummer. See, I can move the mouse. That's always cool. What do you guys think? Do you have trouble moving the?
Did you just try clicking?
I did. We're having a technical difficulty. Ah, I understand. I got it. Yeah, we just. There we go. that was the last slide of the PowerPoint presentation, so it wouldn't advance beyond that. But now we're on the first slide, and it's going to help a lot better. Actually, this is the second slide. Because what I want to do is I want to touch back on some of the things that I've talked with you about last Thursday and then also on Tuesday, and remind you that before you even started to take this class, many of you, most of you, answered these pre-quiz questions. And looking back, it occurs to me that a lot of what I did on Tuesday, talking with you about the chemistry of water, was unnecessary because 75% of you, okay, 73% of you already knew the primary point about pH. So I ask you, what's the deal with an acidic solution? And again, that's what this whole lab is about this week, is the answer I'm looking for there is acids have a higher concentration of hydrogen ions than neutral or basic solutions. Okay, so again, you guys are already with me on a lot of this stuff. For those of you who didn't know, for those of you who did not know, now you know. In the lab this week, we'll strike that home. But again, on Tuesday I talked with you about wet chemistry. I talked with you about acids and bases and how it is that water acts so well as a solvent. And this is going to be an important topic for today as well. So here is another quick look at some of the compounds. So a compound is an assemblage of atoms. Here's a quick look at a couple of the compounds that we've already talked about. And when this topic first came up, I told you one of these things wasn't like the others. I'm going to ask you right now, stop for a moment and think, which one of these four compounds isn't quite like the others? All right? There's a number of ways, obviously, in which they differ. The atoms that are involved are different. The number of atoms are different. But there's one thing more than anything else that I hope you guys gravitate to when I ask you, how are these molecules different? And that one thing, and I'm going to try to condition you to think this way, because I'll tell you, I'm going to be flashing you the structure of molecules a lot during the course of this semester. I'm just going to flash them up on the screen, and I'm going to take you by the hand talking with you about them for a while, but eventually I'm just going to get to the point where, see that molecule? You know the rest of the story. I don't need to explain to you what's going on. I want you guys to be able to look at a molecule like the four that are up here and very quickly, on your own, make an assessment about one thing more than anything else. And that thing is this. Take stock of the kind of bonds. And really what I'm looking at here is I'm hoping you can just do a real quick, it becomes intuitive. It's part of the way you think. You look at it and you say, whoa, that's a lot of nonpolar covalent bonds. Or, whoa, that's a lot of polar covalent bonds. Or even, hey, that's not even a bond, that's an ionic bond. It's not a covalent bond, it's an ionic bond. Those are the sorts of things I hope you really key in on, because from a chemistry perspective and also a biology perspective, that is what tells all the rest of the story. So here, one of these four compounds has nonpolar covalent bonds. Has polar covalent bonds. Three of them have nonpolar covalent bonds. Check it out. Hydrogen, a gas, it turns out. There's one bond. That bond, you guys probably don't need me to tell you, but I'm going to shout it out. That bond is like the poster child for nonpolar covalent bonds. Okay? The reason for that is because the hydrogens, there's two atoms here, they're the same atom, right? And that atom has the same electronegativity as this atom. So that translates directly to the fact that there's an equal sharing of the electron between those two atoms involved in this covalent bond. Equal sharing of the electron means nonpolar covalent bond. Okay? There's a lot of energy here. If you were to break that bond, combine that hydrogen gas with something like, say, oxygen gas, put a match to a mixture of those things, you know what you got? You got rocket fuel. You're going to blast off. That's going to be a big explosion. It's a big explosion because when you're breaking those nonpolar covalent bonds, you release a lot of energy. With me? Nonpolar covalent bonds have lots of energy, and there's another thing about them that we'll get to in a minute that also makes them important to recognize. So I've already mentioned oxygen just a few seconds ago. Here's the next one down on the list. Again, this is a poster child example of nonpolar covalent bonds. For goodness sakes, one oxygen molecule atom has the same electronegativity as another oxygen atom. They have the same electronegativity. They will share electrons equally and harmoniously between them. That is a nonpolar covalent bond. That's also a high energy bond, just like it was for hydrogen. We'll skip over water because that's the oddball here and go down to methane. Methane is again a circumstance where when you look at that structure, all that you have to see are covalent bonds between atoms with the same or exceedingly similar electronegativity. Hydrogen is half empty, half full, just as likely to give up an electron as it is to take one on. Carbon, half empty, half full, just as likely to give up an electron as it is to take one on. You make a bond between hydrogen and carbon. That is a nonpolar covalent bond. That's a high energy bond. If you put a match to methane, particularly in the presence of oxygen, and you break those bonds, you release a lot of energy. For goodness sakes, that's why they sell methane and ethane in containers for you to use to deliver heat, to heat things up, barbecue grills and such. So, nonpolar covalent bonds, these are high energy bonds. And in addition to that, take note, I've already mentioned this, but take note of the fact that those three things that we've just been talking about, those three compounds, are all gases at room temperature. They're gases because there's nothing but nonpolar covalent bonds. They're gases because there is nothing that this molecule needs or wants from anything else. It's a package unto itself. It's satisfied those two rules that nature has. Outermost shell completely open, or either completely empty or completely full, rule number 1. And then no separation of charge, rule number 2. That's all that nature requires. There's nothing hydrogen gas needs from anything else to make nature happy. And so there's no, and this is the key, let me emphasize it, there is no basis at a molecular level for that compound to interact with anything else. It doesn't need anything. It doesn't have anything to bring to the party. It's a package, neat and complete to itself. It doesn't need to be associated with any other compounds. That's what gases are all about. Okay? And again, one of these three things isn't like the others. There's the sore toe poking out at you. Water has covalent bonds, sure, but check out those covalent bonds. They're between hydrogen and oxygen, 2 of them, right? Oxygen, so far in this class, is the most electronegative atom that we've really spent time talking about. I also talked with you about chlorine, but oxygen, it's hungry for electrons. It bumps into a hydrogen, and the hydrogen says, oh, you like my electron? Yeah, fine, go ahead, take it. I'm good with that. I'm happy now that it's not here anymore. I'm empty. Nature's going to like that. And so that electron, because it's a polar covalent bond, spends more time with the oxygen than it does with the hydrogen. You end up with a partial separation of charge. The hydrogens have a little bit of positive charge associated with them. The oxygen has a little bit of negative charge. That is a molecule that has adhered to the letter of nature's laws, right? Outermost shell of electrons completely empty or completely full, not a lot of separation of charge. There is some, but not the spirit of those laws, those rules. And what's going to happen then is there is a potential for one water molecule to interact with another molecule. including other water molecules, so as to be able to satisfy to the letter that second rule of nature that you don't want to have separation of charges. So the little bit of a negative charge on oxygen in water molecules gives them something that can become then the basis of an interaction with another molecule. And the little bit of a positive charge on the hydrogens gives water something that can be the basis of an interaction with another molecule, hydrogen bonding. Right? So water at room temperature is not a gas, it's liquid. Right? And that's because, the difference there is because what we're seeing are at a molecular level are those types of interactions. All right. So there's a picture I showed you on Tuesday illustrating that you can have 4 hydrogen bonds hooking up one water molecule with up to 4 others at any given point in time. And I also showed you this picture, and I told you that water is an exceptionally good solvent. Because of its dual nature, it has a little bit of negative charge, a little bit of positive charge. It's a great solvent. It's got something for just about everyone. If you're an atom or a molecule with a strong positive charge, water's good with that. It'll rub its oxygens up against you. If you're an atom or a molecule with a negative charge, water's cool with you too. Water will hang with you because it'll rub its hydrogens up against your negative charges, and it'll rub its oxygens up against your positive charges. It's got something for everyone. It can interact with anything, including things like sodium chloride, salt. We all know you can easily dissolve a lot of salt in water. Now I hope you really appreciate at a molecular level how and why that takes place. I'm going to pause here for a moment and tell you a little bit of a story. Right? About 5-6 years ago, in the old-fashioned days, back when I lectured with bear claws and stone knives as the implements we had, there were these things called overhead projectors. You may have seen some in a museum or in maybe elementary school. They had some still floating around for you. But this lecture hall used to have 2 really sweet overhead projectors in it, right? One here, one here. None of these fancy projectors that could show color things on the screen and sound systems that can let you play Star Trek episodes. But to illustrate the point of how well water worked as a solvent, I had a clever idea. I had one of the overhead projectors and a beaker of water, right? And if you put the beaker of water on the overhead projector and the light bulb part, it projected up and it looked really cool. It looked like a beaker of water, right? And I took some salt, right? And I put it into the water, and I illustrated to the whole class. Practical in-class experiment. Look how easily the water dissolves the sodium chloride. Right? It's beautiful. I thought it was a brilliant illustration. Worked great. And then I decided never to do that again. Because right after I did that, I got the overhead projector still sitting right there, and I got the water, the salt's there. A student raised their hands, pretty close to the front. Student raised their hands and says, and I'm saying, well, that's odd. I don't get a lot of questions in this class, right? You guys have seen it's such a big class. It's awkward to ask and to stop things. But somebody asks, well, how can I help you? And the student says to me, is that water salty? And many of you haven't seen Star Trek, but I presume you've all seen the Terminator movies, right? The way the robot when you're looking through the robot's eyes, sometimes there's this menu option that comes up. That's going on in my head, right? I got this menu coming up. Is the water salty? And I've got like a dozen things that I'm considering. How do I answer this question? Right? What is the question? Is it salty? Is there some deep philosophical sort of thing that's going on here? I'm just going through, and I go through my list of 12 options for my answer, and none of them are winners. And so refresh, throw those away, give me another, come on CPU, give me another 12, 10 options, something like that. And I do that again, and I'm still coming up with nothing, and I've gone through 2 cycles of this. And so I thought, okay, 3rd time, I only got time here for a 3rd cycle, or this is going to be a real problem, and because this is taking too long. And so I'm churning away, and smoke's starting to come out, And the best I could come up with was yes. All right, let's keep moving, right? So I'm not going to show you how salty the water is, but you know, the water you see over there, that's salty water, right? That's what's going on. That's kind of the whole point. And this slide makes a neat point for me because you guys believe me when I tell you that you can dissolve salt in water. And again, you have experience with this, and you now, I hope, really appreciate how and why that happens. It is salty water, okay? And it's salty water because of these polar covalent bonds, right? This can interact with the positively charged sodiums. This can interact with the negatively charged chlorines. Beautiful. But check this out. Today, I want to talk with you not about the chemistry of water. I want to talk with you really about organic chemistry. That's the chemistry of carbon, the chemistry associated with carbon molecules. And here are some pictures, structural representations of a number of different carbon molecules. And here's the deal. I've told you what I want you guys to do. When I flash a picture like this at you, when you see a picture like this scribbled in with my own hand on one of your exams, all I really want you to be able to do, starting today, but certainly for the rest of the semester, is look at that and make a quick assessment, right? And these shouldn't be things, oh, I'm not that sure. No, you should know right out of the gate, what kind of bonds am I looking at here? And how will that cause this molecule to behave? These are carbon compounds. Again, we're going to talk about organic chemistry today, but check these out. On this whole screen, right? How many? 8 different carbon compounds being projected up there on that whole screen. Do you see even one polar covalent bond? No. Every bond up there is a nonpolar covalent bond, and that happens a lot when you're talking about organic chemistry, when you're talking about carbon compounds. And what does that mean? How does that affect the way that these molecules behave? What are the characteristics of these molecules that are derived from that one observation? Nothing but nonpolar covalent bonds. I'm hoping first you'll think, gee, there is nothing about ethane that water is going to want to have anything to do with, right? That's what I frankly hope is the first thing that pops into your head. And if you're not there yet, bear with me. I'm going to indoctrinate you over the course of today's lecture, in the next couple of lectures. That's the first thing that should come into your head. There's no basis for an interaction between that molecule and water, okay? A secondary thing that might be nice for you to consider, it will become more important the further we get into this course, is, hey, that ethane molecule, that sure looks like it's going to have a lot of energy associated with it, right? If you put a match to that, that's going to burn. That's going to catch fire. That's going to release big chunks of it. It may not even burn. It might explode. Those are a lot of high energy bonds, okay? Nothing that I've said there should be a surprise to you. It's the sort of thing that should follow naturally, logically from the things we've talked about on Thursday of last week and Tuesday. But those are the two features that I hope really jump out at you when you get confronted with structures like this. And this is exactly the way that they're going to show up for you. I'll project them for you. That's the kind of way we'll be looking at and talking about structures. So, 2 things. Not very water soluble, all right? Second thing, lots of energy associated with all of these compounds. And then, if you just want to get extra credit or feel smug about how clever you are, you could add on the third thing. Hey, you know what? I bet you ethane's a gas, right? Because not only will ethane not interact with water, it's not going to want to interact with other ethanes. It's not going to want to interact with, you know, sulfuric acid, you name it. It's just a package unto itself. It doesn't need anybody for anything. It's fine. I'm going to go off over in that corner over there. Okay? And that will be true for propane, which I think you probably have heard of before and which I think you recognize is most commonly commercially available as a gas. It's true for butane, the stuff that lights up lighters if you're a cigarette smoker. It's true for butane if you have a cigarette lighter and you light up cigarettes and such. It's actually also true for methylpropane. And it's true for cyclohexane, benzene, maybe, maybe not. Right? Probably likes to be a gas. The larger these structures become, they start to get an inertia problem, a molecular inertia problem. They're just too big and bulky and long to get enough critical speed going to actually float around. They'd rather just lay flat on the ground. All right, so big carbon molecules, even though they've got nothing but nonpolar covalent bonds, may still become a liquid or a solid just because they're such long chains of carbon. But small ones will be gases. So, if the previous beaker had salty water, do you need me to tell you what happens when you put oil with water? Think about the structure of oil at a molecular level. It's a carbon chain with a lot of hydrogens dangling off of it. There's no basis for interaction between those kind of molecules and water, and what will happen? They will avoid each other. There will be an exclusion of one relative to the other, and this might be news for you. You can share this with your friends and family back at home, but you learned an important thing here this morning. Oil and water don't mix. Another one of those drop the mic moments, right? I've delivered something profound to you. This will be important to you for the rest of your life. I accept that you probably knew that already, right? But maybe before today, you didn't really appreciate at a molecular level why oil and water don't mix. Right? I don't care that oil and water don't mix. I care, and I hope you guys start to care, about the concept, the why oil and water don't mix. Right? Don't be committing to memory little bits of trivia like oil and water don't mix. Rather, try to wrap your heads around the why that oil and water at a molecular level can't get along. Cool? All right. So, here really is the outline for today's lecture. The rest is all sort of prelude, remember stuff. Let me reinforce a couple of points. And if I've done well in the last half hour or so, the rest of this stuff just sort of plays by itself. I just show you pictures. I ask you what's going to happen here, and you come up with the right answer based on everything that I've just been talking with you about. Right? So if things are going well, I don't have to work very hard for the rest of today's lecture. I can sit back and relax. You know, if things start to go poorly, I can crack open a beer. I'm good. Right? So you guys don't have to worry about me. But this is a lecture now, pure and simple, about organic chemistry. So let's talk again about what's going on with carbon. And I want to start by reminding you that carbon plays a really important role on the painter's palette of nature when you're trying to build together molecules. It plays a really important role because it can make 4 covalent bonds. And after that, I'm going to talk with you about some of the cool things, the way you can dress up these carbon molecules in a variety of different ways because of its capacity to make 4 bonds. So we've talked about this before. There are 4 abundant molecules. What was it? 97% of the weight of our bodies comes from these 4 different atoms. Okay? And the reason that we can do so well with just 4 atoms is because each of them has its own special thing. All right? How many primary colors are there? I'm a scientist. I don't worry about that sort of thing. Is it 4? 3 primary colors. See, it's changing all the time. Later on, I'll talk with you about DNA, and I'm going to need somebody to do some research for me and tell me how many letters there are in the English alphabet. Sometimes I go with 26, sometimes I go with 24. I'll need help with that. But apparently there are 3 primary colors. There are 4 different kinds of atoms that we build molecules with. And I love this image of not so much just building atoms as painting atoms, dialing up. Gee, you know, I need something that's small and maybe can make hydrogen bonds. What could I use? Oh, wait, I got hydrogen, right? It's the perfect thing. I got 4 different atoms that we can turn to time and again. And they're special and they do well, those 4 to the exclusion of all others, ultimately because each of them has a different number of unpaired electrons in its outermost shell. Hydrogen 1, oxygen 2, nitrogen 3, carbon 4. Right? That gives me the whole spectrum of the number of different unpaired electrons that I might want to work with. And it gives me some other neat things. One of these things is pretty electronegative. This thing has a tendency to be a little bit electropositive. These 2 things are smack dab in the middle, neither positive nor negative. They're kind of electronegatively neutral. I don't think that's the way it's described by chemists, but I think you get the point. So here is that table of elements that I flashed at you a week ago today for the first time. And I tried to use this to make the point that if you're an atom in the same column as another atom on this periodic table, you'll behave very similarly at a molecular level. The chemistry associated with atoms in the same column are very similar to each other. And that is simply because if you're in the same column, you have the same valence. You have the same number of unpaired electrons. So if you needed to find something to use in place of hydrogen for some reason, lithium would probably be your next best bet. If you needed to substitute lithium for something, sodium may be your next best bet. They behave somewhat similarly. There's a difference between hydrogen, lithium, and sodium, primarily because this is the outermost shell, whereas here we've got some other issues. There's 2 shells. There's a level 2. But nonetheless, they have the same bonding capacity. And if you needed to replace carbon with something, your next best bet unequivocally will be silicon. All right? Because here's just a difference of the level 2 orbital relative to the level 3 orbital. There's a big difference between 1 and 2, not that big a difference between 2 and 3. The valences are similar. If you didn't want to use carbon for some reason, you could plug in silicon. And I've already told you this story, and I tried to get you in the spirit of it by showing you a clip from that famous Star Trek episode involving the Horta that many of you have never seen or heard of before. But there's a close-up picture for you of the Horta. It's in the PowerPoint presentation for today. You can go back and look at it in all of its glory. But as I told you, I think it was a week ago, when the producers of Star Trek responded to the criticism that all their aliens looked suspiciously like humans with a little bit of makeup on, they went to some biologists and said, okay, look, we got to come up with something wildly different from any of the biology we know. What are we going to do? And the clever biologists told them, don't even have it be carbon-based. All the life we know is carbon-based. Have it be silicon-based. And hence, silicon, what's that? Oh, it's kind of like a rock. Oh, okay, their alien became this rock-like Horta creature. And as I told you when I first mentioned the Horta to you, let me emphasize, this is a fictional thing. It comes from Star Trek. This may be disappointing to many of you, but Star Trek isn't real, right? It's a sort of a fantasy. It's a science fiction thing. But nonetheless, it's an interesting idea. And it's plausible that someday we might encounter, as a human species, organisms that don't use carbon and use silicon in its place. But we're not there yet. All right. So, valences, tell us how many covalent bonds these 4 key atoms can make. And let's see what we can do with them. Here are 3 different carbon compounds. You know, I don't want to spend a lot of time on this particular slide. Let me tell you this. Most of the structures that I'm going to be talking with you about, when I show you a structure, I'm going to show it to you like this. All right? The atoms connected, the atoms connected with those lines that are meant to conjure up for you the image of a covalent bond. Okay? So that's these stick drawings is the way that I'm going to be showing you and talking about things. This is an equivalent representation, just doesn't really do as much for you visually. This is also an equivalent representation. It does a little better job of giving you a sense of the geometry associated with those bonds. And this does an even better job of helping you appreciate the geometry. But you can imagine that I'm not going to want to take any time to draw that out on a test. I'm going to always go back to these little sticks, like this, those structural formulas. All right, this is a double bond, by the way. That's a single bond. And just for good measure, all of the bonds that you see here are nonpolar covalent bonds. And now I want to talk with you about the different ways that you can connect all these guys and dress up carbon to do different kinds of things. Okay, so look at the different varieties of carbon compounds that can be made. You can play with the length of a carbon compound, the number of carbons in a chain, for instance. Very easy way to make different kinds of carbon compounds. Ethane, propane, right? Ane describes the common features of these things. Eth is a reference to the 2 carbons in the chain. Meth is what you would use for 1, eth for 2, prop for 3. You guys don't have to worry about those details for this class. It's just I don't want you to be intimidated or mystified if somebody expects you to know that at some point. There are rules to those types of names. But anyway, you can play with the length. You can play with the presence or absence of double bonds. Here you've got some double bonds. Here you don't. And you can play with where along the carbon chain, the string of carbons, those double bonds reside. Here it's in the middle, here it's at the end. Okay? These 2 molecules, actually, these 2 molecules have the same formula, the same number of carbons and the same number of hydrogens, and yet you can see they're recognizably different structurally. These 2 molecules have the same formula, the same number of carbons, the same number of hydrogens, and yet you can tell very easily that they have different structures. Here the chain is one long string of carbons. Here it's got a bend or a branch associated with that chain. When 2 compounds have the same structural formula, when they have the same number of atoms, right, but they're arranged in different ways, we got a fancy word for that. That's called an isomer. One of them is an isomer of the other. Okay, so we've got here, because of these differences in branching, 2 different isomers of C4H, 1, 2, 3, 4, 5, 10, right? C4H10, C4H10, right? But they're isomers of each other because of those differences in the structures. And you can also do things like bend these carbon chains back around on each other to make ring-like structures. Carbon rings typically, at least in living things, typically have either 6 carbons or 5 carbons associated with them. All right? So look at the wonderful ways, the different ways that you can string together and combine carbons to make different kinds of structures. Let's look at them a little bit more closely. I don't think I have anything new or exciting to say beyond what I've already told you about these things. But you can play with their lengths. You can play with their branching patterns. You can play with where it is the double bonds are. And let me just, make sure I mentioned this. This is a really stable situation. It's not like in 2 minutes that double bond's going to move over to there, or this double bond's going to move over to there. Those are locked into place, okay? So these are very stable differences between this isomer and this isomer. And you can wrap carbon chains back up on themselves to make these ring structures. Again, for living things, we're usually seeing rings of 6 carbons or 5 carbons. But it doesn't end there. The sorts of things we've been talking about, for the most part, the kind of isomers we've been talking about, that I've been telling you about, are what could be described as structural isomers, differences in the structure of the carbon chains. There are other kinds of isomers as well. There's this difference here between cis and trans. The 2 C's, so C2, 2 H's, H2, 2 X's, could be just about anything else that you like, right? C2, H2, X2, sort of basic description of these molecules, and yet you can tell at a glance this one's different than that one. There's no rotation around double bonds. They can't spin around. Those are locked into place, and as a result, those are 2 different isomers of the same structural formula. Okay? Chemists call this kind of arrangement cis. So if the things are pointing out in the same direction, if they're going in the same direction, you call it a cis compound. If they're going in opposite direction, that gets the phrase trans. This is a cis isomer. This is the trans isomer of that compound. Okay? You can come up with your own way to remember trans. I don't know of any good ways to remember cis, aside from the fact that it is not trans. Transgender, transsexual, whatever, you know, the crossing over kind of thing, that works well for trans. I don't know what you do for cis, aside from, but there's only 2, right? So if you got trans down, the only thing that's left has to be cis. And then, yeah, look at that. I got close-up pictures of all these things. Then we've got this other kind of isomer, where here it's the same number of atoms in both of these. It's just the arrangement is different. And this type of thing, handedness, is always illustrated, no matter what class you're in, chemistry, biology, physics, it's always illustrated by people showing you their hands. Right? You look at your hands, oh yeah, I see all the similarities. Same number of fingers, same number of thumbs, same number of fingernails, same number of joints, oh yeah. But they're not the same. I can't superimpose. I mean, this hand is clearly different in an important way than this hand. That's what we're talking about here for these enantiomers. Okay, same blue and red stuff going on the picture. It's just they're not superimposable because one is left-handed and the other is right-handed. So there's another example of different ways you can dress up carbon compounds. And I'll tell you, that can have important biological consequences. So you want to buy cheap ibuprofen? Here's what you do. Chemists can mix together certain chemicals to cause them to make compound ibuprofen, right? But it turns out because there's a carbon molecule that's involved, there's this enantiomer difference. If you just do this willy-nilly, mixing the chemicals together, you should get an equal number of the left-handed configuration and the right-handed configuration, the S enantiomer and the R enantiomer. Funny thing, right? Only the S enantiomer, the left-handed version, fits in to a receptor on the surface of some of our cells to tickle those receptors and cause you to get the desired effect from ibuprofen. The right-handed enantiomer can't fit. It's like trying to fit a right hand into a left-handed glove. It just isn't working, and so it floats around and it does absolutely nothing. So you literally end up having to take twice as much ibuprofen to get the desired effect. that you would have if somebody had bothered to make just the S enantiomer. Right? So drug companies actually spend some time figuring out if there are enantiomers, which one is the active one, and then they do a calculation. They determine, does the inactive enantiomer cause any harm? If it does, we'd better not produce any of it, right? And if it doesn't, we still have to do the calculation, is it more cost efficient? Is there a clever way that we can make just the active one as opposed to the inactive one so that we can save on materials and package pills into smaller volumes than otherwise? But so that's what's going on for ibuprofen. You'll see those of you who have had any breathing challenges in the past have probably been exposed to albuterol. Only the right enantiomer works there, not the left enantiomer. I wonder how many of you know this already. The left enantiomer is always referred to as the S enantiomer. The right enantiomer is always referred to as the D enantiomer. This is trivia. It's not going to be on a test. I think it's kind of funny in some level, probably because I'm right-handed. But the left enantiomer gets S because it's short for the Latin sinister, right? Left-handed people were considered to be evil and sinister, right? The word sinister in Latin means pretty much the same as the word sinister in English. So the S is actually short for sinister, left. And right is dexter, dexterous, right? It means pretty much the same in Latin, in English. It's a good thing to be dexterous, and so hence the D or the R for right-handedness. All right. So here is now where the rubber hits the road for this class and organic chemistry. Okay? I think that is the perfect way to describe it. This is where we start to apply the insights that we've talked about. Everything up till now has been frankly kind of boring. Right? Enantiomers, isomers, why do we do this? It's because now it starts to be important from a perspective of a biologist for living things. I got good news and bad news, okay? I'm not sure which to start with first. Let's start with the bad news, right? You guys have seen now how, I think you can start to imagine how you might be able to make a ridiculously large number of different kind of carbon compounds. You could hook the carbons up with double bonds. You can make triple bonds, right? You can hook them up in different ways. You can have them branching. You can have them be circular. You can dress them up with oxygen. You can dress them up with hydrogen or nitrogen. There's all sorts of ways you could combine carbon and those other three important compounds, right? Not quite an infinite number, but way, way more than you would ever want to have to think about. All right? So at a first pass, this might look like this is going to be a real pain. I got to be able to look at a structure, and there's never going to be two alike. Right? They're always going to be different. I got to figure this out every darn time that I come upon some structure. That's true. There are almost infinite ways that you could dress these things up. But here's the good news. Okay? You probably saw this coming, right? Based on the outline behind me, based on what I've just been saying, here's the good news. Nature, for whatever reason, doesn't seem to take advantage of the infinite variety that's available to it. We saw this first in relying upon those four atoms, carbon, hydrogen, oxygen, and nitrogen. How many are there naturally occurring? 92, something like that? A ridiculously large number. Only uses 4 for all intents and purposes, for our purposes at least. There's an almost infinite number of ways you could dress up carbon compounds, right? Lots of ways. Good news. Nature goes time and again back to the same well, actually goes back to the same 6 wells. There are 6 groups of atoms that get attached to carbon compounds over and over and over again. And if you keep your eye on those 6 balls, you don't have to worry too much about anything else that's going to be happening, because those things are what over and over again we find are what nature's using to impart a certain chemical flavor, a sort of shading, a color of chemical reactivity to carbon compounds. That's the list of the 6 of them up there. And I'm hoping, as I'm looking out toward you, that in fact there are 6, there are 7. But one of them is sort of like the absence of the other 6. So I'm still feeling pretty good about 6. Methyl groups are sort of like just the placekeeper. All right? So let's focus our attention on the first 6, and then, oh yeah, by the way, there's the methyl groups. Okay? So here's what's going to happen. For the next 15, 20 minutes, something like that, I'm going to sit down with you. Maybe I will sit down, crack open a beer, and let's talk a little bit about what makes each of these 6, or 7 if you want to be picky, different functional groups of carbon tick. How do they work? Why are they special? What's their job? Again, ultimately, what I'm hoping is going to happen is that in subsequent lectures, I'm going to flash a picture on a screen to you of a structure. I'm going to say, take a look at it, think about what's up with this molecule, and I won't need to say anything. Right? You're going to make a quick assessment as to, is it water soluble or not? Right? Water soluble means that it's got some polar covalent bonds or ionic bonds. Right? You're going to make an assessment. Is it energy rich or not? Does it have a lot of non-polar covalent bonds or not? And now you can add a little bit of nuance and say, gee, what other sorts of things? And those things are going to be derived from these 6 or 7 different commonly occurring functional groups of carbon. Okay, so let's talk about these 6 or 7 functional groups of carbon one by one, tell you what's special about them. And I wish I could do this Socratically, because I think you guys could tell me now and I could take a break, but we'll do it one by one and we'll talk about them. Here's 3 of them, right? Hydroxyl groups, carboxyl groups, and carbonyl groups, not necessarily in that order. What's going to happen is I'm going to talk with you about what the structure itself looks like. We'll talk a little bit about what it is that makes this chemically interesting or distinctive, what sort of characteristics would be associated with this type of structure. And then, I apologize, but there's jargon involved. Each of these different things, not only does this get the name hydroxyl group, things that have hydroxyl groups get called something special. They're called alcohols. So for each of these things, I'm going to tell you the name of the group, point out its structure, we'll think a little bit about its chemistry, and then we'll talk about the trivia, the nomenclature associated with each of them. I'm sorry, but I think you kind of need to know the names of these structures. When I say hydroxyl group, I think you kind of have to conjure up what the structure of a hydroxyl group is. So that's one thing I'm going to ask you to sit down, maybe over the weekend, take a look at these structures and match them up to their different names, right? You should know what a hydroxyl group is. Sorry. And I'm afraid it's probably a good idea also for you to know the names of the compounds. If a compound has a hydroxyl group on it, it would be fair to call that compound an alcohol. Okay? I'm not going to ask you to know the difference between ethanol and propanol, 2 different kinds of alcohols. Maybe in principle you should know the difference, right? There must be a different number of carbons that are involved, but I want you to know that that all, and calling it an alcohol means propanol, ethanol, right? The all, and calling it an alcohol means that there's a hydroxyl group there. So that's going to apply for all 6 or 7 of these functional groups. And what's going to happen is we'll do one by one, functional group by functional group, till we get to the end of the list. Here's the first 3. Here's the next 3 or 4. And let's go. Right? So these pictures come, they're on PowerPoint, right? They're on the pilot page for the course. They're straight out of the optional textbook for the class. You guys don't have to worry too much about scribbling down the details, but I'm not going to stop you if you want to do that, of course. But here's the first one of these 6 or 7 important functional groups of carbon compounds that dictate the chemistry that plays out within the bodies of living things. First one on the list, hydroxyl groups. Okay? A hydroxyl group, it's a simple concept. You got a carbon chain, right? All of these are going to have a chain of carbon atoms, but dangling off of that carbon chain somewhere will be an oxygen that's also hooked up with a hydrogen. A hydroxyl group is simply that, oxygen with one hydrogen, and the oxygen rounds out its need to fill that outermost valence by making a covalent bond to a carbon. Okay? So for all of these functional groups, this last one here that looks like it's just hanging in the breeze, that's supposed to be hooked up to a carbon in a carbon chain on some sort of organic molecule, a carbon molecule. So you got oxygen and hydrogen. When you have that combination dangling off of a carbon, we call that oxygen and hydrogen, that is a hydroxyl group. And hydroxyl groups, when you have a hydroxyl group on a carbon compound, that carbon compound, by definition, is an alcohol. If there's differences in the lengths of the carbon chain give rise to different kinds of alcohol. Methanol means you've got carbon with one carbon with 3 hydrogens and 1 hydroxyl group. Okay? Methanol is 1 carbon. Ethanol, my favorite alcohol, I think everybody's favorite alcohol, whether you've enjoyed it or not, is 2 carbons, right? So 2 carbons, all the rest of the covalent bonding gets filled out by hydrogens, and one of them is a hydroxyl group. So methanol is 1 carbon, ethanol is 2 carbons, propanol is 3 carbons, same deal, 1 hydroxyl group, all the rest of the carbons bonds are filled out with hydrogens. Okay, so those are all alcohols. They get different names because of the length of the carbons that are involved, but we don't need to really worry about that for this class. So I've started with the most boring part in my mind. I've started with the trivia, the names that really don't make a lot of sense. Hydroxyl, where did that come from? Ethanol or alcohol, where did that come from? I don't know. You just got to live with the fact that these are the names that people have settled on for these different things. Hydroxyl groups, alcohols. Let's get to the important part. What's going to happen to a carbon compound that you dangle a hydroxyl group off of? How's this carbon compound going to be different than it would have been if in place of that hydroxyl group there was a hydrogen? Think about it for a moment, right? Scrub away in your minds, scrub away that hydroxyl group. Replace it with a hydrogen. What do you see? If that's what you're talking about, this is a compound that's got nothing but nonpolar covalent bonds. It's got no basis for interacting with water, right? Water has nothing to add or take away from that interaction. That's going to be a gas for whatever that's worth. It's not water soluble, right? First thing to think about, is it water soluble or not? You replace that hydroxyl group with a hydrogen, not water soluble. Unarguably, I hope. And secondarily, oh yeah, this is a pretty high energy compound. Okay, it's got lots of high energy bonds. Put a match to it, it'll probably not just burn, it'll blow up. Okay? It'll release a lot of energy if you break those bonds. But that's not what we're talking about, is it? Stop scrubbing that hydroxyl group out, let it be there, right? That's what we're talking about now. It's not a hydrogen, it's a hydroxyl group. What's up with that hydroxyl group? Does that change the way that that organic molecule, that carbon compound, is likely to behave? We've done nothing to any of these other hydrogens or this carbon. Nothing has happened there. But what do you think? If you've got an oxygen there, I sure hope you guys remember and are way ahead of me in saying, oh, that's electronegative. That oxygen's going to want to bring electrons toward itself. Right? That means the oxygen's going to have just a whiff of negative charge, a partial negative charge. Right? Totally consistent with everything I've been saying all along. That hydrogen attached to the oxygen is going to have, as a result of its electron hanging out more with the oxygen than it does with the hydrogen, that hydrogen is going to have a whiff and a subtle odor of positive charge. Okay? There's a separation of charge now between the oxygen and the hydrogen. And let me stretch your minds here a little bit, right? What's going on with the interaction between that oxygen and the carbon? Think about their electronegativities. The reality is the oxygen's going to start sucking away some of that carbon's, the oxygen is going to start sucking away some of that carbon's electrons as well. So the carbon is going to get just a little bit of a positive charge. The carbon attached to the oxygen will get a little bit of a positive charge, just like the hydrogen gets a little bit of a positive charge. And then, you know, if you're a carbon atom like this guy over here, and one of your electrons has been kind of taken away, isn't visiting home that much anymore, what do you think? This carbon now actually it misses that carbon, it misses that electron. It was a happy home, right? And that home has been disrupted a little bit by the oxygen. And what will happen is this unhappy carbon is going to start saying, hey, you're not appreciating your electrons as much as you should. I'm going to show them how to treat an electron right. You come over here, big boy, spend some time with me, and fill the void that's been left by my ne'er-do-well bad electron that's now hanging out more with the oxygen. What's going to happen is there's going to be a dispersal of a little bit of positive charge over the rest of that compound to make up for the fact that the oxygen has taken that carbon's electron from it a little bit more than it should for fair sharing. Okay? So it's not a hydrogen dangling off the end of this carbon chain. It's a hydroxyl group. And that, and therein lies all the difference. To borrow a famous quote, right? That's a different compound. It's going to behave differently than it would have if that hydroxyl group was a hydrogen. How will it be different? It's got a little bit of separation of charge. It also has a little bit less energy stored in it than it would have if that was a hydrogen. But that's a story for another day. Let's focus on the fact that it's got a little bit of separation of charge. We've gone now from a molecule that had no basis of interacting with water to something that water can rub its oxygens up against and something that water can rub its hydrogens up against. All right? Insoluble now becomes water soluble. There's a basis for this to get dissolved pretty easily within a watery environment. And once again, I didn't mean for it to be a prop that I used that much today, but that's why beer has dissolved ethanol in it. If that hydroxyl group on the ethanol molecules in my big beer here were instead hydrogens, they'd be floating around in a gas and not something that could be dissolved and kept in a liquid state. So there you go. That's the story of ethanol. And not just ethanol, all alcohols. And really, primarily, that's what's going on with hydroxyl groups. When you see a compound has a hydroxyl group associated with it, I hope the first thing that comes to your mind is, oh, that's going to be a little bit water soluble, won't it? All right, oh, it's moving in the direction of being water soluble. Is that too much to ask? Seriously, that's what I'm hoping you guys will take away from this. When you see a hydroxyl group, you say, yeah, water can interact there. That could become water soluble, right? It's not ragingly water soluble, but there's a basis now for interaction with water. All right, enough about hydroxyl groups. Come on, guys. We got at least 5, maybe 6 more of these to go, and we only got like 15 minutes. How's this going to work? Well, it's going to work because I don't need to spend as much time talking about the rest of these now that I've told you how I hope you'll think about the first one. Here's a second one. Okay? Now, that thing dangling off the carbon chain is not a hydroxyl group. Hydroxyl groups are an oxygen with a hydrogen. Here, we just got a single oxygen. The oxygen is happy because it makes a double bond with a carbon, right? Oxygen's got a valence of 2. It wants to make 2 bonds. There's no problem with that structural formula, right? The oxygen's cool. It's got 2 double bonds. The carbon's cool. It's got a total of 4 bonds. 2 of them are in that double bond with the oxygen. But if you dangle just an oxygen off of a carbon chain, what we're talking about is putting a carbonyl group onto that carbon chain. And things with carbonyl groups, depending on where on the chain the carbonyl group is, get called different things by organic chemists. If it's anywhere in the middle, it's called an acetone. If it's on either end, it's called a ketone. I'm sorry, this is an aldehyde, this is a ketone. Ketone and aldehyde, okay. So it shows you how much I use these words, all right? But boy, I would trust implicitly whatever's written here on the slide in terms of the difference between a ketone and an acetone. One of them's got the oxygen in the middle of the chain, the other's got the oxygen at the end of the chain. Trivia, right? What does that do to the chemistry of this carbon compound? What do you guys know about oxygens? It's electronegative. Carbon, not electronegative. You hook up an oxygen to a carbon, nothing's going to happen but sucking away that carbon's electrons. That carbon is going to have a little bit of a positive charge. The oxygen's going to have a little bit of a negative charge. Water soluble. Carbon's positive charge is going to end up getting spread across the rest of the molecule to some extent. It'll get diffused across the rest of the molecule, so you'll have a very faint positive glow to the whole rest of the compound, but there will be a fairly localized negative, partial negative charge associated with the oxygen. Water soluble or not, there's a beautiful basis of a relationship with water now. Water's hydrogens would be very happy to rub up against that negatively charged or slightly negatively charged oxygen. Cool? So that's what's up with carbonyls. We're cruising, all right? Check this guy out. What if we, instead of dangling just a hydroxyl group, we dangle a hydroxyl group that also has a carbonyl group with it? We got a special name for that configuration that we're going to call a carboxyl group. Okay? Carboxyl groups are always at the ends of carbon chains. You can't have that in the middle because there's only one more bond left for the carbon to fill out. But you put a carboxyl group on a carbon chain, and what you end up with are compounds that are called carboxylic acids. At the very least, it's going to be an acid. And now that I've tipped my hand and told you it's an acid, I wonder if it's even necessary for me to ask you to stop and think for a little bit about what kind of chemistry is going to happen, but I'm going to do it anyway. Stop and think for a minute. What kind of chemistry, how is this carbon compound going to behave now that you've put a carboxyl group on it? Check out this poor carbon right there. That carbon's getting beat up, right? It's got 2 oxygens. It's happy because its valences are full, right? This carbon got all 4 bonds made. That's cool. But man, it got a bad deal. One of the things that it's bonded to is an oxygen that wants to take its electrons from it. Right? That's a polar bond. You're going to be seeing carbon's electrons spending more time with the oxygen than it does with the carbon. Oh well, I guess that's how it works. How did things play out with its other bond to the other oxygen. Oh crap, it's another oxygen. Why does this keep happening to this poor carbon? There's going to be a pull on the carbon's electrons toward that other oxygen too. But this carbon has already given it the bank, thank you. Its dance card is full. It's already getting its electrons sucked away from the oxygen. And when that second, the double bonded oxygen, when this second oxygen comes saying, hey, Mr. Carbon, give me one of your electrons. I'd like for it to hang out here. That carbon's natural response is going to be something to the effect of, gee, I don't really have an extra electron to share with you. I'm happy to do this covalent bonding thing here, but is there somewhere else that you might be able to get an electron aside from me? That's the carbon talking. And the oxygen, being the sensitive atom that it must be, says, well, I suppose there might be somewhere else I could go to get an electron to hang out with me. Let me talk to this hydrogen. And the hydrogen says, oh, you want an electron? I'm cool with that. Take it, leave it, doesn't matter to me. Take my electron. And here's the thing. It doesn't get shared. That electron's gone from the hydrogen. It spends all its time by the oxygen. And the hydrogen goes off somewhere else. It increases the hydrogen ion concentration of the solution that it is in. That's the definition of an acid. Just as an aside, to make sure we're all on the same page, and it'll help you out with lab, it lowers the pH. It goes from pH 7 maybe down to something like pH 5 or 4 or 3. It's an acid. As you increase the hydrogen ion concentration, you lower pH. So if you put a carboxyl group onto a carbon compound, what sort of things follow from that? What should follow from that is if, boy, this is not just water soluble. Water's going to love this. Water's going to love having a chance to rub its hydrogens up against that beautiful, full negative charge on the oxygen of the carboxyl group. This is seriously water soluble. And it's even more than that, because now we're talking not about a partial charge, but about a full-blown, flaming negative charge, right? That translates into not just water-soluble, but chemically very reactive. Okay, so there's a potential here for this to make or break other covalent bonds. Okay, so it's very chemically reactive. And it's chemically reactive in a sort of negative way. It's intrinsically a negative kind of feature on the surface of this carbon molecule. And that is in contrast to what happens with the fourth in our list of 6, or if you insist, 7, functional groups of carbon, the amine groups. Amine groups have a nitrogen at their core. They get attached to a carbon chain. And the thing about amine groups, once you put that onto a structure, you call the compound an amine, right? The group is an amino group. The compound is an amine when it has that on it. Funny thing about nitrogen with its valence of 3, the way this plays out is that there's room for a hydrogen to come in and join this party and impart, not so much with its electron, but to impart a positive charge. So in the chemical environments of our cells, the pH of our cells, carboxyl groups lose their hydrogens. In the chemical environment of our cells, amino groups pick up hydrogens. Carboxyl groups at pH 7 or so are negatively charged. Amino groups at pH 7 or so, like what's inside of our bodies, are positively charged. What do you think? Water soluble or not? Yes, water soluble. Water's oxygens with their little bit of negative charge are going to love hanging out with now that flaming positive charge of the amino group. That's beautiful, feels real good there. Okay? And just as carboxyl groups with their negative charge are chemically reactive, not only is this water soluble, but now we've got something that is very chemically reactive as well. Carboxyl groups were reactive because they were so negative. Amino groups are reactive because they're so positive. Boy, if you wanted to bring two parts of a molecule together, or if you wanted to connect one molecule to another molecule, here's a clever idea. Put a carboxyl group on one of them and an amino group on the other, and bam, there, that's happiness there. Right? That's going to work out really well. That's one of the ways that nature uses these functional groups, is to facilitate those types of interactions. And in fact, what I've just described, an interaction between a carboxyl group and an amino group, becomes the basis of what we'll talk about in lecture on Tuesday. Those are peptide bonds. It's the bonds between two amino acids. But that's, again, for something that we'll talk about later. All right, hey, I know I only got 5 minutes left, and I've got, what, 2 compounds, 2 functional groups to go. I can do it, right? Here's another one that pops up time and again. Remember those hydroxyl groups that we've talked about so long ago? Get rid of the oxygen, replace it with a sulfur, and now we've got a sulfhydryl group. Instead of a hydroxyl group, this is a sulfhydryl group. And if you dangle a sulfhydryl group off of a carbon chain, that carbon chain now gets called a thiol. That's the name for those kinds of compounds. Alcohol if you have a hydroxyl group, thiol if you have a sulfhydryl group. Just some old guy wisdom for you. Let me tell you, thiols invariably stink like nothing you've ever encountered before. If you've been sprayed by a skunk, or you've got a pet that's been sprayed by a skunk, thiols are what's going on there. They literally stink, okay? But that's not that important, just a little bit of side information for you. Here's the thing about thiols, sulfhydryl groups. What do you suppose is going to happen here? You dangle that there chemically, what's going to go on? It's going to act in many ways like a hydroxyl group. So there's going to be a little separation of charge, some negativity associated with the sulfur, positivity with the hydrogen and the carbon associated with it. It imparts a little bit of water solubility. Okay? But the big news for thiols and sulfhydryl groups is that it's possible to make a bridge between one part of a molecule and another part of the molecule, or one molecule and another molecule, by getting rid of the hydrogen on the 2 sulfhydryl groups and making a covalent bond between the 2 sulfurs. You can't do that with oxygens because of the oxygen's electronegativity very well, but you can do that with sulfurs. And so those are disulfide bonds, and you can make some pretty stable covalent bonds that cross-link one molecule to another. If you're interested in changing the curliness of your hair, there's something important for you to read here on this part of the slide. It's all about that, but we don't need to get into that detail today either. Here's the last of the big 6 players. The last one is a phosphate group. Okay? It's called a phosphate group because, surprise, there's a phosphorus in it. Okay? I told you a week ago, don't worry about valences and orbitals for things beyond the 3rd. Well, here's one time when it does sort of pop up. All I want you to see when you see a phosphate group is this. If you see a phosphate group on a compound, oh, there's a phosphate group. That compound is phosphorylated. Okay, that's the way we would describe it. But here's the thing. Think about the chemistry. Look at that structure. The example, glycerol phosphate that they give you there. Do you notice the negative signs next to the 2 oxygens? There's no little Greek letter delta squiggle thing going on there or there. Those are full-blown negative charges. Not partial negative charges, full-blown negative charges. And on top of it, full-blown negative charges right next to each other. Talk about something that's offensive to nature. Nature doesn't like to have concentration of like charges. Those things don't want to be near each other. Oh my gosh, this is hugely water soluble, right? And also hugely chemically reactive. It is a honking beacon of negativity wherever it is that it gets associated. It's going to be calling to positively charged amine groups from across the room, come out and hang with me. I got something that'll satisfy you, right? That's serious negative charge. To round things out, the last one is this methyl group. It's just the absence of all these other chemical groups. Not very water soluble, lots of energy associated with it. If you needed to make a hydrophobic, a water-fearing pocket on the surface of a molecule, a good way to do that would be to put a methyl group there. Okay? I think that's my last slide for you. And in fact, there's that lecture outline again. That's right where we started today. What's going to happen on Tuesday is I'm going to show you now how to build really cool molecules from these building blocks. I feel like it's Thursday. Have a good weekend. See you next week.